Welcome to the Explainer. Today, we're skipping the basic arithmetic and jumping right into a pretty mind-bending mathematical journey. We are heading straight to infinity by exploring the fascinating and honestly sometimes wild world of sequences of real numbers. Right off the bat, let's hit on a massive question. What actually happens when you count forever? Does it lead anywhere concrete? I mean, is infinity just this chaotic void, or are there hidden, predictable structures out there waiting to be mapped? Well, here's our roadmap for this explainer. We'll quickly look at what sequences are, chase down their limits, unpack the mathematician's toolkit, and finally figure out how to actually tame the infinite. Let's get into it.
Starting off with Section 1, what are sequences?
You probably already know a sequence is essentially an ordered list of numbers, but formally, mathematically, it acts as a super precise pairing mechanism. You take your natural counting numbers, 1, 2, 3, and pair each one with a specific real number. It's absolutely not a random pile of digits. It has a strict, unbreakable order. And we generally categorize the common ones based on how they grow. Arithmetic progressions grow steadily by adding a constant difference, kind of like walking up a staircase with perfectly even steps. Geometric progressions, on the other hand, multiply by a constant ratio. They scale up or down dramatically, literally like a population that doubles every single year. Moving right along to Section 2, chasing the limit. This is where things get really interesting. When we map out a convergent sequence stretching toward infinity, you'll see the terms honing in on a definitive destination. The curve flattens out, picks a target, like the number 1, and just sticks to it. It settles down. But in stark contrast, you have divergent sequences. These are the rebels. They might oscillate wildly, bouncing back and forth between 1 and -1, for example. Because a sequence like that constantly flip-flops, it has no single limit. It essentially just wanders forever, completely unresolved. So what's the actual formal rule here? Well, a sequence converges to a limit if its terms get arbitrarily close to a specific destination the further out into infinity we go. Meaning, if you pick a large enough starting point, every single number that follows becomes practically indistinguishable from that final limit. To be rigorous about it, mathematicians use a target zone called the epsilon band. In analysis, that Greek letter epsilon just represents a tiny, allowable margin of error around our target limit. To translate that intimidating mathematical definition into plain English, the numbers in a converging sequence eventually get trapped inside that epsilon band, and it can never escape. Literally, no matter how incredibly thin you make that boundary around the limit line, the sequence will eventually enter it and stay inside it forever. Now that is true convergence. Okay, on to Section 3, the mathematician's toolkit. What do we do when these sequences get complicated? First up, the limit laws. Think of these as your algebraic cheat sheet. They let you break down terrifyingly complex sequences by simply adding, subtracting, multiplying, or dividing the limits of much simpler ones. As long as the individual limits exist, you can just pass the limit operation right through the algebra without a second thought. But hey, sometimes a sequence is just too wild or messy to measure directly. That brings us to a frankly brilliant concept, the squeeze theorem. Think of it literally like trapping a fugitive. If you have a tricky, unpredictable sequence, but you can tightly squeeze it between two well-behaved outer sequences that both converge to the exact same spot, well, your tricky middle sequence has absolutely no choice but to go there too. It is forced right into the limit. And for those completely stubborn sequences that hand you confusing nonsense forms like 0 divided by 0, L'Hopital's rule steps in. It gives us a concrete step-by-step method using derivatives, which, remember, just measure the rate of change, to bypass that infinite roadblock and reveal the true limit hiding underneath. We are in the final stretch, Section 4. Let's use all of this to actually start taming the infinite. To do this, we really have to understand behavior and boundaries. We call sequences monotonic if they only ever travel in one single direction, either strictly increasing or strictly decreasing, and they're considered bounded if they're physically trapped by a hard ceiling above, a floor below, or sometimes both. Which brings us to an absolute golden rule in mathematical analysis. Every bounded monotonic sequence is guaranteed to converge, period. If a sequence only goes in one direction and it eventually hits a strict boundary, it has to settle on a limit, even if we don't immediately know what that exact number is. It can't reverse, and it can't cross the line. Lastly, let's talk about recursive sequences. These are super interesting. Unlike a standard formula where you just plug in an n, every new term here is built directly out of the previous one. Give it a starting value and it triggers a mathematical chain reaction, building itself step by step. To find where a recursive sequence ultimately lands, the trick is amazingly elegant. Just assume it already converges to a limit. Let's call that limit L. Since the terms get infinitely close to L anyway, you just swap out the sequence terms in your formula for L, and boom, you have a beautiful algebraic equation to solve. By following those exact steps, a highly complex, infinitely repeating recursive sequence can beautifully collapse down to a very simple single number, something as perfectly clean as the square root of 3. We literally use our toolkit to find absolute order amidst infinite repetition. Which leaves us with a fascinating final thought. We know for sure that every convergent sequence must be bounded. But as we saw with those bouncing, oscillating sequences earlier, not every bounded sequence converges. So, if that's the case, what other invisible boundaries exist in the mathematics of the universe just waiting for you to discover? Thanks for hanging out with me on this explainer, and keep exploring.